but Ben Strader from EFI University. And Ben's going to talk about EFI considerations in high RPM engines. So looking forward to this. It's been a great day so far. So how's your day going, Ben? Are you there?
Oh, I'm doing great. Can you guys hear me all right?
You betcha. Loud and clear.
Good. First try and everything.
Nice view on your screen. Where's that?
That's just here in our little, kind of our classroom office, whatever you want to call it. But yesterday I was sitting in my actual office and I noticed the background was pretty boring. So I thought it'd be more fun to sit out here where there was colors and shapes and stuff to look at. So.
Well, maybe we'll grab a fishing pole after your presentation. It looks pretty inviting.
Say when. I don't go many places without one in my truck, just in case I got to pull over somewhere. So I'm ready.
Super. All right. Well, I'll let you do your thing.
Okay, very good. Let me see if I can get this PowerPoint up and running. So, and you guys just tell me if you can see that okay, and I'll start the slideshow from there.
Looks good, Ben.
All right. So, all right, great. So, hi everybody. I'm Ben Strader, and here with EFI University. I got to do a little introduction earlier. But I know a few people have probably joined in since then. So here at EFI University, we are first and foremost basically a training school. We really want to help other people, get better, especially in racing and motorsports. So we're not really in competition with some of the other places, the sort of mechanic tech schools, the UTIs and YOTechs and stuff like that. We kind of see ourselves in alignment with them and not in competition. So what we really do is focus on the real motorsports oriented type stuff. And I started it back in 2003 with the idea that engine builders wanted to know about EFI and fuel injection tuning. And we've been pretty successful. I think we've taught our courses in about 9 or 10 different countries around the world and had just thousands and thousands and thousands of people learn about engine tuning. Including us. So along the way, we've really had the opportunity to work with high-end racing teams, manufacturers at the OEM and the aftermarket level, much like a lot of these guys that have been presenting today have been in lockstep with us the last 5 to 10 years in developing our program and sharing information. So as we learn more things, we refine and renew our curriculums, and we try to stay on the cutting edge as much as possible. So to that end, about probably 5 or 6 years ago, we started an engine development program here where we could share some of that high-end engine stuff with end users. And my goal in that program was not to teach a class on how to build engines. It's not, here's how a torque wrench works and this is how you put the gasket on the right way. We kind of assume that people come to our program have already been doing some engine stuff and probably already, have some idea about that stuff, but really want to take it to the next level. And so I joke that we teach the things we most want to learn. And for us, that's, engine development work. And so quite often, there's rarely ever a light switch that you can flip where you find 30 or 50 horsepower on an engine combination. It's almost always working hard and you find 3 here and 5 there and 7, and you keep working and you look 12 months later and you go back and say, wow, now I'm 50 better than I used to be, but it didn't happen overnight. And so a lot of that goes along with this high RPM adventure that I've been on for a few years. And to be honest, most people probably know about us or our school because of the publicity we've got from the Spinal Tap project, which I'll talk a little bit, in our thing here. And I know Billy and Lake and Keith and everybody's kind of mentioned too. But that didn't happen overnight either. That started as kind of a hold my beer moment. Billy and I were standing around at one of the PRI shows. And I think it was after NHRA kind of came out with their new rule to limit the engine speed for the pro stock guys. And of course, Billy's been working with a lot of those teams forever. And at that time, I was working with some of the teams helping with the transition to EFI. And we kind of joked like, 10,500 RPM, like anybody could do that. Hold my beer. I bet we could do that with an LS engine. And so we kind of laughed and said, well, maybe we could do that with an LS engine. And that kind of started the whole thing. And it really was one of those things that we kind of looked at each other and shrugged our shoulders and said, how hard could it be? I mean, we'll just put more cam in it and rev the thing up a little bit. Well, turned out it was a little tougher than that. And we didn't really think of everything on that project. In fact, it wasn't like we built it and just said, boom, there you go. It's one of those things where you build something, and that's the whole concept of our engine development program. You build something and you sit back and evaluate what things went wrong. It keeps throwing problems and challenges at you, and then you back up and figure out solutions, and you solve that and you move to the next thing, and there's this whole series of dependent events that happen. And so we had a lot of adventures along the way to that. And so when you guys asked me to get involved and do a presentation, I thought, I think maybe I should share a couple of the hoops that we had to jump through or challenges that came up for somebody else that might say, I want to go beyond the normal engine that does, 5,000 RPM or 6 or 7 or, even higher. So because we specialize in EFI and because we specialize in engine development, I feel like we're uniquely situated to share some of that information. And so considerations for operating very high-speed engines with modern EFI systems was what I put together for you guys. And so we are the home of Project Spinal Tap, which was and is the world's first inline LS7 engine to exceed 11,000 RPM. And I'll put in hashtags on purpose. Like we didn't accidentally go there and miss a shift or something like that, but we took an inline, not a canted valve, it was a parallel valve deal, and we worked on it and worked on it and worked on it. We finally got there. And so I'm sure that at least a few of you have probably seen some of that, but I thought we tried this yesterday and it was a little tricky on the technical side to get the sound right, but I'm going to try to show you guys a little video here just so you can hear the sound of it. And so what I did is I made a little video where we focused in on the actual laptop data, and we'll play it through and see if this works for you guys. So there's kind of a shot looking down into the engine. Now when we ran this thing for real, after all of the spintron testing and all the mocking up and assembly and disassembly and checking stuff, we put it on the dyno and actually ran it. And the beginning of the dyno pull, now when we talk about high RPM engines, I think I forget, somebody Lake or Keith mentioned earlier, like you don't start at 3,000 RPM, you start up close to where you're going to be. And so most of these dyno pulls that we do on engines like this are typically already starting the dyno run beyond the RPM where peak engine torque happens. And so we're not that interested in that area, because other than when you let the clutch out, you'll never see that RPM in a true drag race, say like a comp eliminator or pro stock application. We go to 10.5 and you make a gear change and only falls back to maybe 9,000, even though the engine might make peak torque at say 8,000 RPM. So to avoid stress on the engine, you typically start a little higher. So the shot looking down in the throttle bodies of that engine there, and we started the dyno pull at 9,000 RPM and went up from there. So let's try this real quick. You can see here, you might be able to see my mouse. We're basically in a high idle situation, waiting for water temp and oil temp and pan vacuum, everything to build. And hopefully you can hear the sound here when I play it, and you can see the beginning of the pull at 9,000, and then it revs up at about a typical dyno pull rate of like 600 RPMs per second. So let's see if this will play and let us hear it. All right, so hopefully you could hear that. I've probably only listened to that 6 or 7 million times because the sound just never stops being cool. And I saw it in real life. So hopefully you guys like that. Hopefully you could hear it actually. So if you didn't hear it, somebody may sure let me know and I'll figure out how to play it again. But so here's another example of an engine that we just recently did. That was an EFI conversion. This is a naturally aspirated small block Ford engine. It made peak power at over 10,000 RPM and over 3 horsepower per cubic inch naturally aspirated, very serious piece. But what's cool about this engine is we use some prototype Holley 4500, what they call sniper throttle body injection units. They flow about 1,400 and 14 CFM each, so we had plenty of airflow. But we're kind of moving into this era where we've been told forever that EFI will never make as much power as carburetors. And so I kind of I've had to look at that so much over the years and shake my head and go, but in fairness, nobody's ever done a real comparison of, where the fuel's coming from. And so what's unique about the Holley new Sniper throttle bodies is that the fuel that is discharged from them, if you look in there in the little inside those bowls, the injector bowls, there's injectors inside those, but they spray into like a little annular discharge ring, and the fuel is distributed all the way around the throttle bore. So when you look down inside them, there's no booster venturis to get in the way. And Billy kind of alluded to that earlier, where in a traditional carburetor, we're very concerned with airspeed through there to try to make sure we're metering fuel out of that venturi correctly. And the downside to that is having that booster venturi there hurts airflow. For a much smaller butterfly size or throttle opening, we can end up flowing a lot more air. The challenge has always been, how do we get the fuel high enough in the system that we get that benefit of evaporation and cooling effect so we can make the power that a real carburetor would make. So for the first time, we were able to actually run an engine and make more power with the EFI system than it made with a carburetor. So we were really, really excited about that project. And it was just phenomenally good from beginning to end. And so I just thought I would share that with you. So it's no longer just EFI as, injectors down in the ports and we have to give up a bunch. We've been working for quite a long time now on these really high RPM engines using EFI. And so what are some of the issues with high RPM? Well, I chose 3. There's probably lots more that get overlooked, but I think there's 3 areas that sometimes people don't really think about or consider. And so I thought I'd build a little time to talk about each of them in there. So the first one is triggering. That's how we actually get the engine speed and position to the computer that's going to control things. After triggering, we have ignition dwell. If you're familiar with the old school, like a distributor that had points in it, dwell is kind of how long we have available to charge the coil so we can get enough energy. And then after triggering and dwell, we have the injector, what's called the dead time, and the offset. And these are all contributing factors to what makes it difficult to do these extremely high RPMs. So let's take a look here. So starting with the typical trigger system, what you'd have is a trigger wheel, what we'd call the reference. That would be like your RPM signal that's on typically the crankshaft. And then some engines also use a cam trigger, which we'd call a sync, because what it does is it synchronizes the position of the engine. So if I know where, for example, number 1 cylinder is relative to top dead center, what I don't know if I'm only looking at the crankshaft is whether I'm on the end of the exhaust stroke and the beginning of the intake stroke at TDC, or whether I'm at the top of the compression stroke and ready to start my firing stroke at TDC. By adding the cam sync, we can tell which half of that engine cycle we're on, and then we know how to fire which coil and which injector in the sequence of the engine. So we'll point that out again later when we talk about the idea of sequentially firing a system. And typically you would have either a magnetic or what's called a Hall effect sensor pickup. Those both have pros and cons, but generally what happens is if you're working on an engine, quite often people end up using whichever type came on the engine from the OEM. And so unless you're building an engine from scratch and you needed to choose, there's not really a ton of upside or downside that really makes one far superior to the other. Both can be used successfully. So typically what that would look like is you'd have a crank sensor here that's mounted physically to the engine block somewhere, and then on your crankshaft you have a wheel that's turning with some predefined teeth, the number of teeth, position, so on and so forth. And remember, that gives me my engine speed and position, but not necessarily the phasing of the engine. So I know where I am relative to TDC, but I'm not sure which TDC it actually is. By adding that secondary sensor, it does the same thing, but this one would be on the camshaft. And now I have a recognizable event, because remember, our camshaft is only spinning half the speed of the crankshaft, and therefore that event would occur less often, and so we can arrange a trigger pattern that makes sense to the ECU to work out where we're at there. Not all engines use those. In fact, the vast majority of pushrod V8 engines in drag racing do not use a secondary cam sensor, because it's just more stuff to bolt on and more wiring to have problems with and things that can fail. So the vast majority of engines use some crank trigger and then typically an ignition distributor. So there's no need to know where the camshaft is because the rotor in the distributor is phased to always point at the right cylinder. And so we're going to look at that here in just a little bit. And since they're not trying to fire fuel injectors in any particular order because it's carbureted, they don't need that cam sensor. So the crank trigger or the ref sensor, it sits in close proximity to that reluctor wheel as we saw, and it provides angular position measurement to the ECU. Your computer would be programmed then with the tooth locations and the number of teeth. And so you'll hear people use terms like LS1 uses a 24X trigger and an LS3 or an LS7 uses a 58X trigger. And what they're talking about is the number of triggering events that are on that crank wheel for one revolution of the crankshaft. So the computer needs to be programmed with the tooth locations and the number of teeth in order for it to accurately understand where the engine is. So then these time-based measurements are calculated to report the engine speed relative to TDC. And what do I mean when I say time-based? Well, many traditional systems, you guys have probably seen an MSD flying magnet. So generally with a flying magnet, you have 4 magnets on the actual crankshaft here, and then we have our pickup sensor down here that's located in proximity to the pickup, so the wheel. So from a physical measurement standpoint, we only get an event every 90 degrees. So when I say time-based measurements, we can actually calculate the time between any 2 events and be able to work out pretty quickly how fast the engine's actually turning and whether it's speeding up or slowing down, so we can predict the right time to, say, fire a coil for a sparking event or maybe even a fuel injector or whatever. But in truth, most of it is based on an accurate guess of working out what the engine speed is after we physically know the position every 90 degrees. So when we put more teeth on the trigger wheel, we get a higher position resolution, but obviously that also requires more computational power. So for example, a stock GM LS, ECU or engine control unit typically limits the engine speed to approximately 8,000 RPM. It goes a little more than that on some, maybe 8,100, 82, but not much higher than that. So in order to make an LS style engine go above that low 8,000 RPM range, the first thing that we had to do was we had to dump the factory ECU and go to an aftermarket computer that was capable of much higher RPMs. There are a lot of things you can change and retune and reprogram in a factory stock ECU, but the hard RPM limit is not one of them. It's hard coded in the ECU and it's not easy to change that. So we did that when we were working on Project Spinal Tap, and after all the work and endeavors and the day that we finally got it running was such a wave of relief that ran over me of, oh my gosh, after all these years, 2 or 3 years of work, it's finally happening. And I'll never forget the first time we revved the thing up, it was like, it's going up. We started 8,000 or 8,500 or something, the thing's going up, and all of a sudden, bang, it just hits the rev limiter. I'm like, man, I feel so dumb after all this time. I forgot to raise the rev limiter, and we hit the limiter at 9,200 or 9,300, and I was like, man, that was a waste of a run and time on the valve springs and whatever else. So of course I go into the computer and I start looking and I go, well, that's weird. That I didn't actually forget. The rev limiter was set at 11,000+ RPM. And so we started looking into it, and we realized that we were actually losing our crank trigger signal in that 58X or 60 tooth wheel, mostly due to Hall effect sensor saturation. So to give you an idea, there's a look at the factory GM LS3, LS7, 9A, all of them. It's got 60 teeth on this wheel. They call it a 58X because there's 60 total teeth that are evenly spaced. But then what they do is they knock 2 of them off, so that every time that missing 2 teeth passes the sensor, we'll know where we are relative to TDC. If I just had 60 evenly spaced teeth, I could count the engine speed, but I wouldn't know the engine position because there's no way to differentiate which tooth actually lines up near TDC. So by having a missing gap, it's really 58 events and 2 missing, so we call it 58X. The nice thing about that is we have 6-degree position resolution because you have a 360-degree travel and there's 60 teeth, so it works out pretty nice to have a really fine resolution. So you got to ask yourself, why wouldn't you want that? Well, you would want that if you were running a normal vehicle. GM and Bosch and all the other manufacturers that make those kind of wheels. They do it mostly so they can have more finite control of the engine, specifically in reference to things like exhaust emissions. It's easy to detect a cylinder misfire if I can see the engine's accelerations and deceleration rates more often than, say, every just 90 degrees of crank travel. So not only can we see that the engine's speeding up or slowing down, but you could say, for example, I know that in one engine revolutions, there should be 4 excitations of the crankshaft. Every time one of the piston fires, it should speed that crankshaft up a little bit. So if somewhere around the revolution, somewhere around the circle, we see a dip in engine speed or a deceleration, we could work out pretty quickly that somebody didn't do their job and one of those cylinders probably misfired. And we can even tell which one it is if we know where it was in the firing order. So at an OEM level, that high position resolution makes a lot of sense. However, when we get into this really high RPM stuff, here's an example of what a healthy trigger would look like. So you're looking at an oscilloscope trace of a 68X crank trigger with a single long or wide tooth camshaft sink event. That'd be like a typical front mounted LS1 style or LS2 style camshaft trigger. And I don't know if you can see my mouse here or not, but the yellow ones represent the little 58 teeth, and then there's a gap, and then 58 teeth and a gap. But what you'll notice is the camshaft trigger here only happens every other gap, because remember, it's turning half of the crankshaft speed. So now we have a way to tell one of these gaps happens when the cam sensor is high, and one of these gaps happens when the cam sensor is low. So now we can differentiate not only that the gap happens X number of degrees before top dead center, but we can tell you which one of those is near top dead center on the compression stroke, so we know it's time to fire a particular spark plug. So that's what that looks like. But what will happen on a typical Hall effect sensor like this, it's a little hard to see in this diagram. So what I'm going to do is zoom in a little bit for you. And you'll see here that while these typically are supposed to look like square waves, they get a little bit rounded on the rising edge. The slope here gets a little worse as the frequency or how often we're triggering it goes up. You can even see it here on the camshaft trigger and starting to happen. And even if I go back a little bit, you can now look in that blue one, you can see it a little bit there. But notice the falling edge of that trigger is very sharp and very square. Well, our crank triggers tend to do the same thing. So first of all, when you're using an aftermarket EFI system, it's important to understand that if you hook up your crank trigger sensor, you typically have some flexibility to choose. Should I use the rising edge or should I use the falling edge of the trigger that the tooth on the wheel creates? Well, if you're going to do some high RPM stuff, you really want to make sure you're using the falling edge to trigger your events because it's much closer. So what will happen is we go higher and higher in RPM. These triggers are coming faster and faster in frequency. And so this edge gets more rounded and more rounded. And when that slope gets really steep down here, you can fall below the triggering threshold for what your ECU sees as an actual event, and it can get filtered out. And when that happens, you get into a situation where it will just drop a cylinder or cut or misfire, and it will fool you, like it did me, into thinking that you are sitting on a rev limiter when you're really not. So, so what's the right answer? Do I use a 4 trigger and give up my resolution? Or do I use a 58X trigger and have all the revolutions but have this high-speed issue? Well, we ran into this problem in 2016 and 2017 when the NHRA Pro Stock teams went to EFI. Everybody on the surface, wanted the high resolution, but what we found is we got into issues where that could be a problem. And so we tried a bunch of different wheels. We tried 8 teeth and 12 teeth and 24 and 36, you name it. And what we found was the 36-1 or 36 evenly spaced teeth with 1 missing was a great compromise, because with a 36-1 wheel, we get every 10 degrees of resolution is now possible, but we could do a lot more total engine speed with a 36-1 than we could going to a 58X. So with the 58X, we get a little bit more resolution, but at the cost of a lot lower total RPM capability. Whereas when we were going from a 4X tooth to a 36x tooth, we get a ton more resolution. And so just as an example, if you could do 9,200 RPM with 60 teeth, and that was roughly what the limit was, well, if I cut those teeth down to only 36 events per revolution, that's 67% more RPM I could do. So by going to a simple change like going to a 36-1 trigger, we could theoretically do 15,300 and even more RPM. I say theoretically because none of us had the bravery to actually try it, and nobody missed a gear to try it on accident, but suffice to say it has no problem going well over 11,000 RPM like we did on the Spinal Tap project and on most of the high RPM engines that we use around here at EFI University. If it's below 9,000, we'll typically use the factory triggers with no issues. If it's going to be above 9,000, we save ourselves the heartache and we just cap off that rear crank trigger and go ahead and bolt a 36-1 on the front, and it solves the majority of our issues before they become issues. So that's a little something from me to you that will save you time if you decide you want to get into this high RPM game. Just use as much resolution as you need, but not more than you need because it can get you. So there you go. So that's just a little insight on what we learned from triggering. So let's talk about the ignition system then. So traditionally, your ignition system would have a single coil and a distributor, and you might have individual coils per cylinder nowadays with a more modern system. So the question becomes, well, what's the advantage? It costs a lot more. Why would I want to do that? I got more wiring, more things that can fail. So, we could get the location relative to TDC and use that to determine the firing position for both my ignition system and my fuel injection system phasing. And we can fire each ignition event and just let the distributor sort it out, and then the spark plug gets its spark because where the rotors phase. So a lot of people do that, where they'll run, even if they're doing a throttle body type EFI system or maybe carburetors, but they want to run, a distributor. It's easy to do that with a crank trigger and not need a cam trigger. So a lot of people do that. And what we're talking about here when that happens is when we go to charge the coil, we talked about dwell earlier. A lot of people say, what's dwell? Well, it's the time that it takes the coil to charge from your primary, your battery voltage, to the secondary level. And that typically takes between 3 to 5 milliseconds to fully charge. So we're talking about thousandths of a second. So in the graph here, you can see on an oscilloscope, from when the circuit begins to draw current as we charge the coil. When it goes flatline up here, we call that saturated. So holding the circuit on to charge the coil longer than that point doesn't do anything for us in terms of potential spark energy, but it does tend to overheat the coil and the wires and stuff like that. And so there are physical limits to how long you want to charge the coil, but there's also requirements for how long you need to charge the coil. If you run out of energy here, so if I started charging this coil and I stopped in the middle before I reached the peak, I wouldn't have the maximum energy available to fire the spark plug. So maybe that's a problem, maybe it's not, but I'll show you, for example, this is, I don't know if you guys can see this or not, a typical modern, this is what they call the Mercury Marine or the smart coil that's used in tons of different applications. I don't have one of the old-fashioned coils to show you because I was born in 1976 and we're not using antique stuff anymore. Anyway, what happens is the construction of the coil has a big influence on how long you need to charge the coil. So the number of windings, how much iron's in there, as well as how much primary voltage you have. If I have a 16-volt system or if I have a 12-volt system, or for that matter, if you have a low battery and you only have 8 volts to charge the coil, it changes how long it takes to reach full spark energy. So let's think about that a minute. In order to give full spark energy to the cylinders, we're going to need somewhere between 3 to 5 milliseconds to charge each coil. So I got 8 times I got to fire if I have a V8 engine. So that means 3 times 8 is 24 milliseconds, and 5 milliseconds times 8 is 40. So I need somewhere between 24 and 40 milliseconds worth of time to actually charge and fire all the spark plugs with maximum coil energy on a V8 engine. So in our little graph here, you can see the dwell time is how long I'm actually charging the coil from B to C basically, and A, I fire the thing. And now that I'm done, I can rest between A and B in my idle time. I can rest for however long is available before it's time to start charging again for the next event. So thinking about that for a minute, how long does an engine cycle actually take? Now, when I talk about an engine cycle for a 4-stroke V8 engine, remember I'm talking about 2 revolutions of the crankshaft. The first one fires half the cylinders, second one fires the other half. So here's an easy math problem for you to remember. If you want to know how much time it takes for an engine cycle in milliseconds, that's in thousandths of a second, all you have to remember is this easy little formula. It's 120,000 divided by the RPM. Go ahead and try it. I'll wait. All right, that's long enough. You guys are taking too long. I'll just give you an example here. So using that math problem, at 6,000 RPM, we have 20 milliseconds. But at 10,000 RPM, because the engine's turning faster, it only takes 12 milliseconds. And at 12,000 RPM, it only takes 10 milliseconds. Now think about that for just a second. Let's talk about 6,000 RPM. What's actually happening in an engine cycle, right? So we got to start at top dead center, and the intake valve opens while the piston begins to move down. So that creates a larger volume in the cylinder, which lowers the cylinder pressure. So we have a differential across the intake valve that will then cause air and hopefully fuel to start moving into the cylinder. So that piston's going to go all the way down to the bottom, and then it's going to start going back up and start compressing that mixture. And at some point, we're going to close the intake valve so that no more air and fuel can get in and no more air and fuel can get out. And we're going to continue compressing that mixture until somewhere near top dead center, we're going to light the spark plug a little bit early. That's what we call spark advance, to give the flame a little bit of a running start and get an advantage to burn all the mixture in the chamber. Now that burning mixture starts to expand and it puts power and energy against the piston. That pushes it back down in the bore. It's putting leverage against the crankshaft, but the whole time my volume's getting bigger, so I'm losing pressure. Somewhere near the bottom half of that stroke, or getting close to bottom dead center, we're going to open the exhaust valve and start moving exhaust out of the engine. And then the piston's going to get to the bottom and stop, and it's going to start coming all the way back up again and start pushing that air out the exhaust valve because of the higher pressure being created by the lower volume. We get all the way to the top, and hopefully we'll have a low pressure there in the exhaust system that will help draw some of that air out and scavenge the cylinder, and then we'll be done and we can start over. So I had to do intake valve open, increase the volume in the cylinder, flow air and fuel in, get it all in and trap it. I had to close that. I had to compress the mixture. Then I had to spark it and light it on fire and create a combustion event, push down on the piston to create power and energy. Then I had to try to get rid of it all and empty the cylinder out. Now I had to do all that at 6,000 RPM in only 20 thousandths of a second. It took longer to say 20 thousandths of a second than it did for that to actually happen. Now consider when we did Spinal Tap, I had to do all that same stuff at 11,000 plus RPM, but you're literally filling and emptying the cylinder, and you're literally opening the intake valve more than an inch of lift 95 times per second. 1/1000. That's it. 95 times that just happened. So when we put that into the perspective of what a high RPM engine actually looks like, sounds like, and what's going on, it's really interesting to imagine all the things that need to happen in the perfect order and sequence in the little tiny amount of time that we actually have. But this formula doesn't just work for nice round numbers like 6,000, 10,000, and 12,000. You can do anything you want. You could say, how long does an engine cycle take if I was doing 5,374 RPM? You want to know? Take 120,000, divide it by the engine speed, and you'll know. So that's for you. You'll really use that. You'll really like that if you use it more in the future. So as you can see then, if I have a single coil, even in the best case scenario where it only takes me 3 milliseconds, let's say, to charge my coil, and I got to charge it 8 times, that's 24 milliseconds. Well, at 5,000 RPM, the entire engine cycle takes 24 milliseconds. That means with a single coil, after 5,000 RPM, I'm no longer able to completely charge and discharge the standard old-fashioned, points ignition or HEI style ignition coil. We physically do not have enough time left in the engine cycle to do that. Now, traditionally, the way to overcome that is start with a huge excess of coil spark energy, more than we actually needed to get the event done, so that as I'm losing some, I don't fall below the required amount that it takes to actually light the cylinder. So you can see here in this slide, some of this can be overcome by using an ignition system that starts out with a large excess of energy, such as an MSD like capacitive discharge ignition system. And basically what would happen there is The CDI stores energy in capacitors and can have a much higher primary voltage delivered to the ignition coil much faster, so we have more excess of time available. But even though our RPM is going up and up and up and up, I'm still going to have more ignition energy than I actually needed to fire the spark plug, so I can kind of get away with that time, as Billy calls it, the time-space continuum. And so while we could solve that distributor-based problem with a CDI, and we could get the spark energy we need, we still have a physical limitation by using a distributor rather than individual ignition coils. That maybe isn't a problem for a naturally aspirated drag racer, but if you're doing nitrous, if you're doing some form of boost with a procharger, supercharger, or a turbo, quite often you have pretty extreme swings in what you want to do with your ignition timing that are limited by the physical travel of the distributor and the rotor phasing inside the distributor. So by going to individual coils, then we can use a cam sync instead of just having a crank trigger and a distributor. If we use a cam sync, since we know where we are within the engine cycle, we could tell if I'm on the exhaust stroke or the TDC compression stroke. So now we can fire each coil and fuel injector simultaneously and in order, in the correct firing order. So if you think about that, where I had one coil that I needed to fire 8 times in one engine cycle, now I have 8 coils that individually only need to fire 1 time per engine cycle. So 1 divided by 8, obviously you get the idea. I have 87.5 more time for the coils to rest and be able to recharge. So in terms of doing high RPM, high energy type ignitions, you know, the benefit that we gave up by not having the high energy CDI capacitive discharge ignition systems, which in fairness produce a very hot spark, they do it for a very short duration. And so what can happen at extreme engine speeds is, even though I get a very hot spark from a capacitive discharge ignition, the actual spark event only lasts for, you know, 1 or 2 or 3 degrees of crank rotation. So if anything happens with your mixture distribution inside the cylinder where you miss it, you're out of luck. You're going to have a cylinder misfire. Even though the inductive style ignition systems like our smart coils, even though they technically have less energy available than a traditional CDI would have, they typically will discharge that spark across the plug gap at, say, 10,000 RPM for something in the order of 14 or 15 total crank degrees. So you might get 6 to 7 or even 8 times as long of an opportunity to fire the mixture because of the length of time it takes the spark to jump across the spark plug. So I'm a big fan of using these smart inductive style coils in a high RPM application because I have enough spark energy to do the job. I get a long spark duration to give me the most opportunity to make sure I get the mixture lit, and I get a lot of time to be able to make sure that coil is fully charged. So a great example of a way to use modern technology in a high RPM engine. So here's an example of individual coils in each cylinder. It gives us the ability to have extreme advance or retard functions, such as doing boost enhancement or smoother rev limiting. A lot of people say, what do you mean by rev limiting? And if you think about what's happening to the engine and the crankshaft, if you're at 10 or 11 or who knows what RPM, and all of a sudden you start banging the rev limiter, the amount of torsional twist that happens to the crankshaft because of one cylinder that's not doing its job, or 2 or 4 randomly. So we're pounding on the crankshaft and the counterweights are doing their job to try to keep everything in balance. And then all of a sudden I don't for a couple of times. That twisting motion of the crankshaft takes a beating, and so does everything else behind it, drivetrain and everything. So by being able to do some of our rev limiting by retarding the ignition timing, much like an OEM strategy, we can limit the engine's torque output temporarily with a 1 cycle or 2 cycle retard function rather than simply a cut and chopping that cylinder off. So we get a lot of advantages to the individual coil per cylinder type application in a high-speed engine that aren't necessarily showing through on the surface if you were only to look at the spec sheets of how much energy this one has and how much energy this one has. It doesn't really show up until you actually start doing this stuff. So there you go. Hope you guys like that. So let's talk about our fuel injectors. And I know I'm going kind of fast, and I'm not trying to buzz through it or gloss over information, because I'm sure there'll be some questions, but I want to make sure we get through it, give you guys lots of time to enjoy and talk and ask questions. But one of the big ones that pops up a lot is what happens to the fuel injectors in a high-speed engine, especially when we do this without a cam sync sensor. So let's talk about it a second. So the injector is really a solenoid valve. You have fuel coming in the top, and we have a valve that closes it. We have a electromagnetic coil here, the red part in the middle, and we energize that coil, and it becomes magnetic, and it draws the valve up off the seat. But remember that it has to do that against our fuel pressure too. So the differential pressure across the nozzle of our injector has a big effect on its performance, as well as how strong the magnetic field is in the injector. So when we talk about injectors, a lot of people talk about the injector size and the flow rate of the injector and pulse width and duty cycle and all these different things. But the one that I want to focus on for just a minute here is called duty cycle. And if you're not familiar, I want to simplify it for you, because the duty cycle of an injector is the comparison of the flow capacity of the injector to what your engine actually demands. So there's more technical ways to describe it when we talk about the relationship of injector pulse width to time per engine cycle and all that. But bottom line is, if you just think about it like this, the more horsepower your engine makes, the more fuel you're going to require. So, you've got a dyno graph here. Whether I make 1200 horsepower at 6,000 RPM or 12,000 RPM at 8,900 RPM or 9,800 RPM or 18,000 RPM, the reality is 1,200 horsepower requires a certain amount of fuel. So that being said, here's an example. Let's say I have a V8 engine and I have 8 injectors. Now these injectors, here's one, and here's one. They flow 80 pounds per hour each. That's what we call the slope of the injector. So since I have 8 of them and each one flows 80 pounds per hour, we could assume that I'm going to have a total of 640 pounds per hour of fuel flow available to give my engine. So what determines how much of that fuel flow the engine's actually going to see? Well, the answer is how much power you make. So let's say we have an engine that makes 1,200 horsepower. Now this 1,200 horsepower engine has a brake-specific fuel consumption of 0.45. If you're unfamiliar, brake-specific fuel consumption is a measurement that we take that shows us, for the amount of fuel we actually consumed, how much power did we actually make. So a typical high RPM, naturally aspirated, high compression engine, they'll be 0.45 or better. Most of the time even better than that, but this is a good example. So let's say I need to feed a 1,200 horsepower engine, and it needs 0.45 pounds of fuel for every horsepower per hour. Well, doing some quick math, if you multiply 1,200 times 0.45, you see that we're going to need 540 pounds per hour to feed the demand of that engine. Make sense? All right, so now let's compare how much fuel we need to how much fuel we actually have available. So in the next slide, we're going to need roughly 84% of the injector's capacity. Regardless of what engine speed we're talking about, we're going to need 84%. But percentages and real actual time, they're not the same thing. So let's take a look at what I'm talking about. Now, the slope of the injector determines how much time it will take to deliver the required fuel flow. So when I talk about that, what I mean is, we said the injector flows 80 pounds per hour. So since the slope is assumed to be fairly linear, it should then, if it gives me 80 pounds in an hour, it should be able to give me 160 pounds in 2 hours. And for that matter, it should give me 40 pounds in half an hour. And again, assuming our slope is linear, which at least in the usable portion, we're hoping that it is. But what I'm getting at is the slope is a linear amount of fuel delivered the more I increase the time that I turn the fuel injector on for. But pulse width is what we use to determine how long the injector is turned on for. So I'm going to have to give this injector a pulse width that will deliver the required amount of fuel to feed that engine's 1,200 horsepower. The question becomes, how much time is available to give it that pulse width? And the answer is, well, it depends on your engine speed. So let's take a look. So the injector is a solenoid valve. Here's the problem. Being a solenoid valve, the valve takes time in order to respond to a command. So for example, in our drawing here, what I have in blue is a theoretical pulse. This is the command where your computer turns on and says, hey, start flowing fuel. It goes bang, and it holds it on, and the distance that it holds that on in time is called pulse width. So theoretically, in my mind, I think, okay, the longer I hold it open, the more fuel it flows. And for the most part, that's true, except for the fact that if we go back and look at our injector, you can see that this magnetic coil needs to energize once that signal command comes, and that magnetic field needs to draw that pintle or that valve up off the seat, and that doesn't happen instantaneously. So because it doesn't happen instantaneously, we have a little bit of time where the injector misbehaves and doesn't do what we tell it. So we call that offset or dead time. Now, what affects the offset and the dead time are primarily three things. The physical makeup of the injector. How heavy is that valve in there? So take a look at this injector here. I hope you guys can see that. And then take a look at this injector here. This one has really lightweight, small components inside of it. This one has rather large, big components inside of it that allow it to flow a lot more quantity of fuel. But as you can imagine, the heavier those components get, the longer it's going to take before that injector can physically respond to that command impulse. Now that I got it all going and I say, okay, I'm good, stop, you can shut off, just be done, it takes a little bit of a time to put the brakes on and shut everything off as well. So the physical construction of the injector has a huge outcome on how much that dead time is. The next thing that affects the fuel injector is the actual fuel pressure that you're putting in this thing. If you put more and more and more force down in there trying to hold that valve closed, it's going to be more and more difficult to get that valve to open against the pressure. So fuel pressure will affect your actual dead time. And last thing will be battery voltage. The lower the voltage you have, the longer it's going to take and the less strength your magnetic field is going to have to be able to move that injector off the seat. So those are three things that are going to affect how much dead time we actually have. So when we look at that, here's an example of a dead time or a flow data sheet. This I stole from the guys at Injector Dynamics right off their website. So it tells me that they have an ID 1000 part number, and this is the dynamic flow data. Now, over here on the far right side, what you see is the actual slope, or what people would call the flow of that injector. You'll notice that the slope increases with more fuel pressure. Makes sense, right? If you had a garden hose and you turned up the water pressure, more water is going to come out in a period of time. But you'll notice that the offset here, which is in the table, and it's plotted out in microseconds, which we need to move our decimal place to get milliseconds. So for example, here at 40 PSI differential fuel pressure and 12 volts, we have 1210 microseconds. That would be the same as 1.2 milliseconds, okay? But what you'll notice is that for any given voltage of the battery, as my fuel pressure goes up, the delay or the offset that it takes to make the fuel injector open gets stronger, gets longer. And sometimes if we have a really low battery voltage, like over here at 8 volts, we get to about 75 PSI, it just plain won't open at all. So the dead time goes to infinity and you get zero flow out of that injector. So you'll notice that the higher the battery voltage is and the lower the fuel pressure is, the faster the fuel injector can respond. And so they give us this data so that what we would do then is program that table into our fuel injection computer. The computer will then reference the battery voltage and the fuel pressure at any given moment, and it will calculate how much fuel requirement the engine has so that it can work out what the pulse width needs to be to deliver the fuel. Now, we would typically call that the effective pulse width. The problem is, to get my effective pulse width to equal what the engine's demand is, I have to add the lost offset or the lost dead time. So when I take my effective pulse width, and I add in the required amount of offset time based on fuel pressure and battery voltage, what I get is the actual pulse width that's delivered to the injector, so that I might have to deliver, 10.5 milliseconds in order to get 9 milliseconds worth of actual flow out of the injector. So that's an important differentiation that a lot of people misunderstand. But when you start doing very high RPM engines, it becomes very critical. And let me show you why. So traditionally, people would say that you should limit your injector's duty cycle in an engine to 85%, and nobody ever really questions why that is. I hear people say things like, oh, it's because you don't want to overheat the injector and whatever, and it's like, no. You have a cooling medium flowing through the injector all the time anyway with your fuel. It's not about overheating it. It's about making sure that there's enough physical time left in the cycle to make the injector behave. So I'm gonna draw a picture for you, or with my words anyway, and let's use an example. So let's say I got my fuel injector, and based on my battery voltage and my fuel pressure, it has an offset or a dead time of 1 millisecond. Now, 1 millisecond that's only 1,000th of a second. It's not that much time, but every time we fire this injector, we're going to lose 1,000th of a second. So since that's a pretty small amount of time, it almost doesn't matter. And since, I don't want to add a lot of complexity to my system, I'm just going to ignore the cam sync. And what I'm going to do is just run a crank trigger and fire the injectors however I need to. So let's find out, what is all this dead time actually going to cost me in real numbers? Well, there's two ways that I can deliver the required fuel. Remember, it's required. I have to get that fuel into the engine. Otherwise, I'm going to be calling up Lake and Keith over there for a new set of piston rings after I lean it out and burn this thing up. So we want to keep that cost down. So we got to make sure we deliver the required amount of fuel. The engine is demanding that fuel, not asking for it nicely. It's saying, I got to have it. So a typical fuel delivery system, you got your tank and a strainer and a fuel pump, and it goes through a filter, and you have a pressure regulator that's keeping our pressure where we want it, and we have fuel injectors. So the fuel injectors turn on and off to deliver the fuel, and there's a couple different ways that we can manage the injectors that we have. Assuming that what we have is more than one fuel injector, we have to decide, do we want to fire them all in a sequential order, one at a time? Well, that's ideal, but we need both a crank and a cam sync sensor to be able to do that, so we can fire them individually within the firing order and place them at the right time in the cycle. But again, that cam sync, it adds a lot of complexity, and I just don't want to deal with it. It's more money. So there's nothing wrong with doing what's called batch fired injection for most engines. Now, in a batch fire system, we don't need the cam sync because we're just going to fire the injectors every revolution of the crankshaft instead of every other revolution in the firing order. What we're going to do is I'm going to cut the time that I fire the injector in half, but I'm going to fire it twice as often. So there you go. I get the same amount of fuel, half as much, twice as often. Everybody's happy. Well, let's think about that. So that means if I do that, though, on every engine cycle, since I turned the injector on twice, I had to pay for the offset and the dead time twice. So here's the deal. We are going to assume we have an injector with a dead time of 1 millisecond, 1,000th of a second. So that means we know from earlier that we had a 1,200 horsepower engine and it had a 0.45 brake specific. I'm just going back to our example. So we have 8 injectors. They flow 80 pounds per hour. So we have 640 pounds per hour available, and we need 540 pounds per hour. So we're going to need 84% of the capacity. In other words, I'm going to have to use 84% of the time available in the engine cycle to be spraying fuel. So that means whatever the engine speed gets to, I got to make sure that there's a minimum of at least 2 milliseconds left over to accommodate the offset or the dead time of my injector. If I don't, I will start cannibalizing my fuel flow into my dead time, and I will no longer have precise control over how much fuel the engine actually gets. So let's go back and look at our earlier example where I had 6,000 RPM. Well, that takes 20 milliseconds. So that means if I take my 2 out, I'll still have 18 milliseconds available to be able to spray fuel. At 10,000 RPM, there's only 12 milliseconds total available. I still have my 2 milliseconds worth of dead time because it's 1 per fire and I'm firing it twice per cycle. So then now I take my 12 and subtract 2, I'm only left with 10. At 12,000 RPM, it gets worse. I only have 10. I take my 2 out, now I've got 8. So using a little bit of algebra, we can go in and figure out, well, if that's the case, if you want to do this without a cam sync sensor and you're going to batch fire your injectors, you're only going to be able to get to about 9,600 RPM before you lose control of your fuel injectors. At 9,600 RPM, using our little formula, 120,000 divided by the RPM, we can see that there's 12.5 milliseconds available per engine cycle. So if I take my 2 milliseconds out for my dead time, since I'm batch firing this thing twice, that only leaves me with 10.5 available. Well, 10.5 available, 10.5 worth of flow out of 12.5 available, that's my 84%. So if I start increasing the RPMs above 9,600, I'm going to take my 2 milliseconds worth of dead time out, but then I'm not going to have enough time left to accurately flow all of the fuel the engine needs. So high RPM engine operation gets tricky if the dead time of my injectors are really large. So the question becomes, what are you going to do about it? Well, if you're the kind of guy that just runs big block Chevys, old school, and you want to convert to EFI and it's going to go in a boat and you're only going to see 5,500 RPM max, it's really not a problem for you. Forget everything I said and don't worry about it. Just go about your way and enjoy your day. However, if you're like me, you know, 5,500 RPM is just kind of high idle. We're just waiting to start the dyno pull at 8,500 or 9,000. And so we actually have to pay attention to stuff like this. And ask me how I know, I'll be glad to tell you. So the question is, what do I do about it? Well, first and foremost, I could change to a sequential operation by using that cam sync sensor, because now I'm only going to fire the injector once per engine cycle. That means instead of having 2 milliseconds of dead time total, I'm only going to have 1. So I've cut that offset in half. It allows me to increase the range I can get to. The other thing I could do is I could use a larger flowing injector, because then the amount of time that I'll need to hold the injector open to supply the required amount of fuel that the engine needs will get smaller. So if I have an injector with a larger slope, I will need less time available to do the job. Or instead of using a 12-volt battery system, maybe I go to a 16-volt. You'll remember that the amount of time that it takes to offset the injector is dependent on battery voltage. So the more voltage I have available, the less time I have to waste waiting for the injector to respond. So then obviously I got more RPM capability available to me. Lastly, choose an injector that inherently has a lower offset. If you can find one that has a low enough offset, that has a high enough slope to give you the amount of fuel your engine requires, it's a great fix. And so all of these are things that we needed to do when we were trying to make these EFI naturally aspirated high compression ratio engines go to 10,000 RPM and beyond, because they were things that didn't used to matter, and now all of a sudden they did. So hopefully that was interesting and thought-provoking and gave you some ideas of things that you might want to implement in your own project. None of it's meant to be an absolute. We are always in the research and development learning stage, if you will. I like to say at EFI University, we only teach the things that we really want to learn. So with that, you know, I'm going to open it up and take some questions, and we'll talk about it.
All right, super, Ben. That was a great presentation. That's
Thanks.
something that a lot of engine builders in the shops, and we don't get a chance to see, you know, the stuff that you're showing. It's sort of a, you know, we're learning tooling techniques and honing and that kind of stuff, but to actually learn about what's going on the outside, that was really, really well done. So thank you very, very much.
Yeah, no worries. It's fun to share this.
Yeah, you betcha. What I'll do, I'll go to one question. We'll go one question for Ben, and then just to kind of keep things rolling on time, we do have other questions, Ben, and we'll get to those sort of while we wrap things up here. But the one question I've got that they're asking is, let's see here. Do cylinder pressures increase proportionally with engine speed?
No, most of the time they go down. Cylinder pressure is directly proportional to torque output. So your highest cylinder pressure is typically going to be where your engine makes peak torque. So if you look at like a typical dyno graph, you'll have a peak torque, and then your power continues to go up after that, even though the torque is dropping off. And the reason is that horsepower is a function of how much torque you can do over a period of time. So one of the secrets to making huge power per cubic inch numbers that we typically brag about, which frankly aren't that, you know, valid, is that as we do more RPM, we can get away with less cylinder pressure because we're simply doing it more often. For example, the classic definition of power is torque times RPM divided by 5252. Most of you guys probably know that. So what that really means is if my torque is 500 when I'm at 5,250 RPM, well, divide that by 5250, that means my power is also 500. But if I make 500 foot-pounds of torque at 10,450 RPM, that's the same amount of work that I'm doing every time I fire the piston. However, I'm doing it twice as often. So my 500 foot-pounds of torque becomes 1,000 horsepower at 10,450 or 540 or whatever the number is. So the cylinder pressures in a really high RPM engine, at least a natural aspirated one, are typically quite a bit less than other engines, simply because our volumetric efficiency tends to go down as we have less time to fill the engine with air. We're just making more power because we're doing it more often.